Okay, can you confirm me whether this screen is visible to you or not?
Yes, it's visible.
Okay, okay, thank you for waiting this much. So welcome to the next session, assignment number 10 on course of engineering hydrology. So today we are going to discuss about flow routing. This flow routing can be divided in two major aspects, that is one could be a river, then another one could be a reservoir. How, what are the principle, what are the methods that are related to these concepts, and how we can determine the downstream hydrograph if we are having information of the upstream hydrograph. So there would be some numerical associated with this. We will discuss it during the session. So before going to this discussion, there is one question that was left. uh, this question was regarding the last session, right? Ashish, am I right? This question was left.
Yes, yes, yes.
So the thing was that how can we determine the hydrograph? Actually, in the earlier question, there was a situation that we want to figure it out, the maximum peak discharge, uh, base width, what could be the base width, then what could be the base width for 50% of discharge, then 75% of discharge. But here the question is itself to determine, or hello, anyone is asking something?
No.
Okay, so here the question was about how we can plot 5R synthetic unit hydrograph for the watershed B using Schneider's method. So actually the thing, whatever the procedure we have followed, it will be a same only. Okay, the difference will be the approach, how we can plot it. So I want you to just look at the procedure, how we are going to solve it, and then later you can execute some of the problems for your deeper understanding. Okay, so here the entire question, whatever the plot we have to make, it is divided into 8 or 9 steps, and within these steps what are the major parameters we have to determine, we will look into step by step. Okay, so
Mm.
here you can see first one is watershed A. So here what are the properties that are related to watershed A, it is mentioned here. Okay, basin lag is given, peak discharge is given, area is given, then length of the catchment is given, then length of the catchment to the centroid, it is also given. Then for the watershed B, it is the required hydrograph. For the for A, we already have a hydrograph, unit hydrograph we already have. So how we are going to convert? So I'm sure you will be knowing that we, what we need to do in order to like plot a required hydrograph, we should have two major coefficients, right? Can you name them? In the earlier question we have tried to like compute two major coefficients from the known watershed, and then we are transferring those coefficients to the unknown watershed, right?
Mhm.
Those coefficients
Yes.
were Cp, and
Mm.
one more was, which one? This Cp was related to coefficient for peak discharge. Then there was Ct, I guess,
Mm.
related to time,
Time.
right? So from here we were getting the basin lag time for the basin lag, then time for the peak. We were getting these kind of information, and then using the CP we were getting the information about discharge, peak discharge. So yes, firstly we have to check the whether the unit hydrograph which is given to us, it is standardized or not. So after checking it using the criteria that is given here, it has been found that it is not equivalent to basin lag. Okay, so TP was calculated and it was found to be 34, because earlier it was given basin lag was 35, but since it is not standardized, so TP will be modified. So modified TP value was found. Then in the second step, the coefficients like CT and CP is calculated from the watershed A, right? So you can see CT is computed, CP is computed. What are the parameters we already have? See, what is the procedure that we are looking into it? We already solved in the previous question. So I hope you may be getting the steps directly. I'm not going into the details like how we are going to compute. I just want you to go through the steps. You can directly solve it by your own. Okay, ma'am, are you getting the things?
Yes, yes, I'm following.
Okay, good. Okay, so here in the step second we are going to compute two major coefficients, CT and CP, and then in the third step we will be transferring these coefficients in order to compute the unknown parameters for watershed B. See, watershed B we need to determine the unit hydrograph, so it is a required unit hydrograph we need. Given that we already computed that CT and CP property coefficients we have, so based on that we have computed the basin lag. Okay, so basin lag comes to be 5.48 hours, but yes, of course you can see it is coming 5.48, but we have been given how much? We have been asked about 5 hours, right? You can see here in the question it is asked to determine the SUH for 5 hours, right? So since it is coming more than that, so again we have to make correction in this, and accordingly we have computed the peak discharge. Then peak discharge have been computed per unit area, and time base we have got it for the required unit hydrograph. So based on that we could have idea that yes, how much peak it is going. So we will be having the most like maximum ordinate which it can go, and basin lag we already have the information, so accordingly we can compute the base width, base period, how much maximum width it can attain. Then in order to if we want to plot the SUH, it has mentioned that we should have three major widths. Okay, first one is this entire base period. Okay, time base, we should have this entire width. Then we should also have the width related to 50% of discharge, 50% of peak discharge. So this width we also need to compute in order to plot this graph. And then there should be a 75%, like there should be a width, known width for 75% of discharge, peak discharge. So if we are having these three major width, then we can easily plot this graph, though we have to smoothen after plotting, but yes, this is the step. So here you can see there are certain empirical relations which are given in order to compute the base width for 75% of peak discharge. Then for computing the 50% of peak discharge, it is given here. So using these empirical relation, we can derive these widths. Okay. Now after getting these, you can see the picture here. Now you can have some approximate plot of this SUH, synthetic unit hydrograph. Still it needs some correction. You can't say that yes, whatever the values we are getting, it is correct. Okay, one more thing I want you to note it down, that yes, before attaining the peak, what was the width is taken as 1 by 3, and after the peak it is taken as 2 by 3. We have already looked into these things in earlier session also. So whatever the values we have computed till now, whatever the values related to time, values related to width, width of the hydrograph, those values have been plotted along with the peak discharge, and this graph have been found. Now these are the some details which have been summarized here. Okay, so till now this question ends up here. I hope you are getting the difference. Like there is only one major difference here, is we need to compute these width values should be known in order to plot this graph, else there should be a difficulty. Because if you are only having the time base value, you are knowing the width only, and you are simply saying that I have the peak value of this much. So definitely here also you will be assuming that triangular kind of thing will be plotted. But yes, you know that this triangle assumption kind of thing won't exist everywhere, na? So what you have to do, you have to take some more values between these lines. Okay, so in order to make it possible, these widths at 50% of maximum discharge and 75% of maximum discharge, width have been computed, and then they have been plotted in order to get the smoothened curve. I hope you are getting this. Now we are moving to the questions related to today's session. So the today's session we are going to cover the topic that is flow routing. So I hope you all have gone through this concept, right? Routing. So I want you all to just give me a brief understanding, your understanding, that what you understand by the flow routing. Okay, anyone?
With the knowledge of the upstream flood, getting a hydrograph and the downstream section of a river or any water course.
Yes, right, that's a good one. Anyone else? Ashish, do you have any input?
I think it represents the change of hydrograph when the water move from upstream to downstream.
Yes, right, yeah. So yes, you are right. So here the thing is, after knowing the magnitude and the duration of the flow at one section, we are trying to determine the hydrograph either in upstream, either it could be in downstream. Okay, wait a minute, give me one second only, wait. ओके वो थोड़ा सा क्लास ले रहा था अभी. Hello. Can you see the slides now?
Not yet.
Now?
No.
Not yet. Okay, wait a minute. Okay, it got removed. Ashish, tell me.
Yes, I can see now.
Okay. Yeah. So here the question is flow taking place in a river or a channel from upstream to the downstream, the change that take place in the hydrograph include. So it is saying that if we are having a channel and we have hydrograph at this location and we are trying to get a hydrograph either in downstream or maybe in upstream as well. So what could be the possibility? What kind of things can exist? That is the question.
Floating in river channel of zero this is not include. Increase in peak.
Okay, increase in peak, good.
Stream to stream.
Anything more? Ma'am, from your side, any response?
Peak can get delayed also.
Yeah, right. Okay, so there could be, if you are looking into the aspect that we want to determine the hydrograph at the downstream or maybe an upstream, definitely there could be a certain watershed characteristics as well as the flow characteristics which would influence the shape of the hydrograph, right? So if I'm saying that there is a river channel where the flow is going from higher elevation to the lower elevation and either the width of the river is going to be increased, okay, or there could be a certain kind of depression in the same channel. There could be a possibility, right? So in that case, what you will see that width of the channel as well as the depression, it will be acting like a just kind of reservoir kind of thing. It will be storing a certain amount of water, okay, and that is why it could have effect in reducing the peak values, okay. So in this case, this whatever the peak you are getting, this certain amount of water have been stored in a term called reservoir, and now you are having some reduced peak values, right? And also whatever the water which is now going to flow after this reservoir, it may be a chance that this graph may also get like this peak, whatever the peak values you are getting, it could have a possibility that it could get delayed also. So in this case, occurrence of the attenuation, see, this entire flow routing concept is much more like, it is much more relevant in terms of reservoir, okay, because once the reservoir is being constructed, the hydrograph will have more impact in its sale, right? Because see, if you are saying that we are constructing a dam, okay, in the river channel in order to hold a surplus amount of water in the upstream side, and then there are spillways where we are trying to divert little bit amount of water to the downstream side. So in that case, this entire concept like flow routing, this entire concept to make big sense in order to quantify the volume of water in the upstream and the volume of water which is passing as an outflow to the downstream side. So in that case, we need to, there is a chance that we need to control the peak flow. So when we are trying to compute the peak after constructing a reservoir, then that word came into a picture called attenuation. So attenuation in peak, that is the one of the word that comes into picture. And then again, the second aspect will be a peak may get delayed, right? So these kind of structure make good sense while we are considering the monsoonal kind of precipitation occurring in any part of India. So in that picture, in that sense, in order to like control surplus amount of water, in order to reduce the flood kind of scenario in the downstream side, these reservoir as well as like peak attenuation, that makes a good contribution. Wait a minute. Yes, sir. Sir, 11, sir. Sir, 11, sir, Vienna. Yes, sir, right. Sir, evening, sir, हाँ, morning में है, sir, early morning 5. Sir, conference, sir, 14, sir. Yes, sir. हाँ सर, वैगनर सर. यस सर, हाँ देखा सर, उसका सर 6 समथिंग 7,000 पड़ रहा है सर. यस सर. यस सर, 11 को मैं कंटिन्यू में निकलना चाहता हूँ सर. जैसे ही मैं लैंड करूँगा उसके बाद कनेक्टिंग फ्लाइट में देखूँगा उधर. यस सर, या सर फ्लाइट से सर. यस. यस सर. यस. यस, राइट सर. यस, रिटर्न सर. यस, राइट सर. यस सर, मैं उनसे बात किया था तो दोनों ही वो लोग एक्सप्लोर करा देंगे. मैं वैगनन पे ही रुकना चाहता हूँ, बट मैं फिर विजिट दोनों जगह पे कर लूँगा. स्टे वैगनन पे. यस. नहीं, वियना से मैं डायरेक्टली वैगनन निकलूँगा जी. सर एम्स्टरडैम ही होगा सर, अभी देखा नहीं है सर मैंने. यस सर. सर जर्मनी, सर अभी प्लान नहीं किया था, वैसे चला जाऊंगा. ओके, राइट. या श्योर सर, दैट्स विल गुड. हाँ यस सर, उनको थोड़ा सा आइडिया भी उनने दे दिया काव्या जी ने. Yes sir, right, Wagner. सर ये तो लगता है उस टाइम पे मैच नहीं हो रहा है, उनने तो मना कर दिया था शायद, हो नहीं पा रहा है। सर इनने कुछ फाइनल डेट नहीं बताई सर अभी भी। हाँ यस सर। यस सर। या हेलो आशीष।
Yes, we are here.
Okay, sorry for the disturbance. Actually, there is some kind of conference have been scheduled where I have to go for presentation. That is Vienna in
Mhm.
Austria. So that thing was I was discussing with my supervisor for regarding some kind of official mail and all. So sorry for the
No,
disturbance.
sir. No issue.
Yeah,
It's okay. All the best.
yeah. Thank you. Okay, so here uh, the thing will be like occurrence of attenuation. Peak will be getting depreciated, and then another one will be a peak gets delayed.
Mm.
Okay, so here from upstream to the downstream flow takes place. So here the thing will be like you can see first aspect is attenuation, and the flow can also be get delayed. And what are the application of this? You can see here that if we are using a flow routing concept, so we can easily derive a unit hydrograph as well as a synthetic unit hydrograph. Then why this flow routing kind of thing is important? So you can see that we can provide like we can design a detention storage in terms of you can say that kind of hydraulic structure. I'm just talking about it. Hydraulic structure could be anything, like it could be a canal also, it could be a culvert, it could be any kind of like a dam we are making along the channel. So in designing those aspects, we should have idea about the peak flows QP with respect to the duration, like duration as well as length, like in the entire channel. If I'm taking a section 1, if I'm taking a section 2, if I'm taking a section 3, so what are the like maximum QP I am getting, and what is the width of river here, and what is the duration, like time to get peak. So these kind of information is relevant in order to design any kind of hydraulic structure, because the thing will be like we have to control the volume of water that is coming as an inflow. So that is a task we need to do it. So here it was also mentioned that control structure, that is also one of the thing flow routing uh, can do. And at the last you can also see if we want to control the flood flows, in that case also flood routing is more important. Okay, now moving to the next question. So it is related to a flood routing. So flood routing through a reach, the point of intersection of inflows and outflow hydrograph coincide with a peak of outflow hydrograph. So it is saying that we are having a flood routing, we are making we are doing a flood routing along a reach, and we have once we have plotted a kind of you can say inflow hydrograph, and then after some time outflow hydrograph have been plotted. Okay, so here you can see there is a some certain kind of intersection which is making between inflow and outflow kind of hydrograph. So
Mm.
this whatever the coincide here, you are getting a point of intersection. Okay, and the thing what is it in mentioning here is that this intersection point is called a q peak. Okay, peak flow of outflow hydrograph. Outflow hydrograph. So where this could okay, hydrograph. So where this possibility could occur. So that is the question. Okay. So I'm sure that you may be getting the words like channel routing, what we call it as channel routing, then flood routing is there, then reservoir routing is there. There are certain assumptions which are holding all these concepts together. So have you gone through this?
No, no.
So here, like you can see flood routing we are plotting here, right? So for this case, option D will be valid. When the inflow is into a reservoir with an uncontrolled outlet. Uncontrolled outlet means whatever the maximum volume of water is stored by a reservoir, that if it is reaches to this level, like I am saying that a reservoir is there, okay, I'm getting that there could be a maximum flood level to which it can hold the water, because after that this structure is not going to bear that pressure, water pressure, it is not going to hold that. Okay, so definitely what there could be some engineer, they are operating some kind of spillway, so they will be diverting that water to the downstream part, right? So there could be some maximum value to which it can store that water. So after that, this entire water, if certain inflow is still coming after reaching a MFL, then that entire water will be diverted to the downstream only, and that could be accounted as a peak flow. Okay, so in that case, that peak will be called as an uncontrolled outlet, because that entire water is now coming as an uncontrolled, because no reservoir, because reservoir is not holding any kind of uh, inflows. That is the thing. So in this case, when the inflow is into a reservoir with an uncontrolled outlet, means inflow is coming and reservoir is not holding any kind of water, because it is already in its maximum level. So whatever the outflow will be there, that will be at maximum value. Okay, so here the thing it was asking that peak of the outflow hydrograph, it should be at peak. So in this case, why like when you are operating this reservoir at an uncontrolled flow, then you will be getting the intersection point at the peak of outflow hydrograph. That is the thing. So look into the some of the explanation here. So firstly, I just want you to see some of the basic concepts. So during the rise of outflow hydrograph, the inflow is greater than the outflow. So in that case, built up of storage in the reservoir will be done. Okay, so it is saying that inflow is higher than the outflow. In that case, built up of storage will be there. If there is a recession of the outflow hydrograph, means outflow is greater than the inflow, in that case water will be getting depleted from the reservoir. So it is saying that depletion of the storage will be there. In the third case, it is saying that when the outflow hydrograph has receded, the reservoir returned to the initial level. So in that case, build up of storage in the reservoir will be done. In this box, you can see there is one important line which is mentioned here: at maximum storage, outflow from the reservoir will be uncontrolled. Maximum storage in the sense reservoir maximum volume to which reservoir can hold the water. If it is reaching that level, outflow, whatever the outflow you are going to see, that could be an uncontrolled way. Like just think of an scenario of flood. Okay, if reservoir is getting water beyond its capacity, then all the operating gates they get open in
Hmm.
order to safeguard that hydraulic structure.
Okay, got it.
So that is why these concepts of inflow routing as well as an outflow routing, okay, that makes a like more sense in that case. So you can see here there is some more keywords have been mentioned here. When we are saying that it is controlled, so water releases through a control gates. Okay, so control from the this word you are getting everything, control gates. So whatever the spillway gate they are working over the dam, they are in the controlled way. But if when we are saying that uncontrolled, because now they are made to open, they are freely operating now, there is no control in the
Hmm.
discharge.
Hmm.
Okay, now moving to the next question. So the question is related to a Muskingum method of flood routing. So can you tell me like you may be having an idea about routing, right? You got the word routing. There are two type of routing we used to perform. Now
Yeah, one is
tell me them.
uh, hydraulic routing. One is
Yes. So hydrologic routing is there, and then
and
another one is hydraulic routing,
yes.
right? And what are the differences? Can you tell them?
I think hydraulic routing use the continuity equation.
What?
Hydraulic routing use continuity equation. I think for
Yes,
calculation.
right. Good one. And then in case of hydraulic routing,
It use both continuity and
continuity and momentum equation.
momentum equation.
And combining both these equations, there is one famous equation that been derived using these two concepts, is that Saint-Venant equation.
Okay.
Do you familiar of this equation? This equation is Saint-Venant equation. This is one of the most widely used, you can say, equation in order to simulate a kind of dynamics of flood wave, right? If any kind of flood is going, and you need to simulate those scenarios in any kind of catchment, you should have like idea about this equation, because every model like you may be familiar of HACRUS. There is one model that used to perform this kind of like flood kind of simulation. So HACRUS, there is one model. Okay, so using these equation in this model, you can simulate the scenarios, that where could be the possibility, that how much time, like if you are having an idea about hydrograph at I'm saying this, uh, that from the origin, like origin in the sense, here the rainfall, maximum rainfall have been occurred, and now you have an idea at the outlet of this basin, that yes, we have received a QP, means maximum discharge of about maybe 15 billion cubic, right? 15 BCM it have been achieved, maybe after, you can say, 30 minutes of rainfall. Okay, I'm just saying in an example. Okay, and now there is one city downstream of this catchment, you can call it as Surat city. I'm just taking an example. There is a Surat city in Gujarat. Okay, it is highly developed, it is an economical backbone of India also. So in order to, like, this entire water will be diverted to a river only. Okay, and this entire, if surplus amount of water is coming directly in the river and going in the downstream side there is a Surat city. So definitely there could be a possibility that entire excess amount of water get uh, diverted in the floodplains of Surat city. Okay, and if there is no control over these river banks, then definitely this entire city will would collapse. So in this case we need to have models, so that we should quantify that if we are getting this much of Q, then by how much time, within maybe 15 seconds or maybe 15 minutes, this entire water which was just generated by this basin by the kind of extreme precipitation, it could move to the Surat city. So what could be the time? So in that scenario we can have some local scale implementation. Engineers could do something in order to prevent or in order to divert that water, though it is most of the time uh, people can't control this flood water. People are working on this domain, but yes, of course, these kind of things are only helpful in order to make a strengthful hydraulic structure only, because with that case only we can prevent the water, we can divert the water. Hydraulic structures, maybe we can divert the water in the canal also, excess water if it is coming. So here the question is like Muskingum method. So tell me what could be the answer. So A option is here, it is form of reservoir routing method. Second one is hydraulic routing method. Then the complete numerical solution of Saint Venant equation. Then the last one is hydraulic channel routing method. So Muskingum method, which option is correct? With reference to this, I can add one more thing. You may have studied two major, like there were two concepts. One was prism storage. Have you studied? Have you got this word or not? Prism storage. And there is one more word, wedge storage. These two words are used in this Muskingum method only. Okay. So this entire Muskingum method tells that what it tells. Any idea? No idea. So here Muskingum method is a form of hydraulic channel routing method, where it depends on what will be the outflow. Outflow will be just having a relation with an inflow. Which kind of relation we will discuss in the explanation. So here you can see routing process is being divided in two major aspects, that is hydraulic, this one hydrologic routing, and then another one is hydraulic routing. In hydrologic routing we are using a continuity equation or flow or storage relationship. This entire concept is a lumped model. So lumped routing in the sense, for the entire area we are getting only a single values. Okay, we are getting a single values only. But if it is saying that distributed, so definitely we are getting a values at some different location also. So here you can also see that variation with respect to time is considered. With space it is not considered. So that is why if we are considering that there is no spatial variation, so that's why in that case lumped word is used. No spatial variation is there. I am assuming that entire basin have similar characteristics. But if I am saying that in the region values are varying with the space, if I am moving from one point to the another point, values are changing. So in that case I will call it as distributed flow routing. And if we are considering the aspect distributed flow routing, in that case you should have idea about continuity equation, momentum equation, and if we combine both of them we can achieve a Saint Venant equation. And it can vary in both space and time. Now if hydrologic routing concept is used. So it is an unsteady process. Why it is unsteady? Because it is not same with the time. With the space it is same, but with the time it is not. Now see the thing. If we are saying that there is a hydrologic system, so input and output as well as the storage, they are related with this continuity equation. This is a continuity equation. Do you familiar with this? See, there are two kind of, like, continuity equation can be divided in two major criteria. If I am saying that steady state condition, if I am saying that steady state condition, like uh, for each time whatever the input is coming, it is going and directly converted into an outflow. In that case, uh, you all have studied that what kind of equation we used to perform. Q1 equal to Q2, right? Q1 equal to Q2. Am I right or wrong?
Yes.
So whatever the inflow it is coming, it is directly going and converted into a
Outflow.
outflow. But if I am saying that it is unsteady, it is changing with the time, then storage concept will be used.
Yes.
And that is why you will be getting the difference of inflow and outflow. It will be stored as an storage. So for these kind of thing, this continuity equation in unsteady case, this is important. And see this storage, how this storage is varying, and it is dependent on inflow and outflow. So this could be expressed in form of this. So after combining this and these two major relations, we can derive the Muskingum equation also. So these two major concepts have been used in Muskingum method also. We will see some of the numericals related to this also. Now, if I am saying that reservoir routing by a level pool method. So if level pool method is used, then in that case storage has non-linear relation with outflow only. So it will be expressed in form of this, S equal to FQ. If I am saying that flow routing in channel, so flow routing in channel can be performed by using Muskingum method, and it is having an storage linearly related to inflow and outflow. So S will be a function of inflow and outflow, just similar to this both these relation, if you combine them, then you could achieve this. So this is combinedly called as a Muskingum method. Then there is one more model called series of linear reservoir model, where storage is a linear function of Q with time derivative also. So just it's for your information, but for this relevant to this question, Muskingum method, so you should have idea that storage here is linearly related to inflow and outflow. Now we are moving to the next question. So I hope you may be getting this directly. So hydraulic routing is governed by
Continuity and momentum equation.
So you are saying that continuity equation,
And momentum
you are
equation.
saying that momentum equation. But I just mentioned that if you combine A and D, you can achieve to one major equation.
Saint-Venant's.
Yes. So for this question, continuity equation, then momentum equation and Saint-Venant equation. These three will be a correct answer. Ma'am, is it clear to you?
Yes, yes.
Okay.
It's clear.
So see, just for the information, these things are already clear to you, that hydraulic routing is only varying with the time, and hydraulic routing is varying with the space and time both. This is a form of Shannon-Twenant equation where you can see the expression for continuity equation, and then you can see a expression for momentum equation, and see different kind of scenarios can be simulated using these relations, continuity and momentum. How you can simulate them? Because if you are assuming or maybe ignoring certain parameters, then you will be having a steady or uniform or maybe a non-uniform kind of scenarios you can develop, and you can implement into your uh, model aspect. So these equations are directly useful while we are modeling a flood, or maybe a, you can say, um, this hydrologic modeling we used to perform, okay, in order to predict the volume of water distribution in the basin, where we are getting a surplus amount of water, where we are getting a reduced amount of water, where we need reformation in order in reservoir operation. In that case also these equations are much more relevant. Okay, now moving to the next question. Here again, I hope you may be getting this question directly. Hydraulic routing is, so just now we have discussed that hydraulic routing can vary with what?
A lumped flow routing.
No, it could be, it won't be a lumped, just hydrologic.
Okay.
Don't confuse this word hydrologic.
Mm.
If it is there, then lumped scenario will be there. Because why it is lumped? Because it is not varying with the space.
Mhm.
See, not vary with space, only vary with what? Time. That is why
Time.
it was mentioned
And
unsteady. But if you are saying that hydraulic, then in that case,
distributed flow routing.
yes, right, it will be varying with space, it will be varying with space as well as the time. Then in that case hydraulic routing is important. So here, don't confuse with this, it is a distributed flow routing, as well as it is complex, but it is more accurate in comparison to hydrologic routing. So see here,
Mm.
if you are talking about the hydraulic routing, then it is more accurate than hydrologic routing. Very useful method in distributed rainfall runoff modeling. See, this is rainfall runoff modeling is nothing but a hydrologic modeling. Most people used to use a kind of water balance equation. You may be familiar with this water balance equation. Okay, so this water balance equation, and they are deriving the rainfall runoff modeling. Now in the third option you can see simulation studies in the catchment. Just I mentioned there, simulation studies have been made. So in order to quantify the inflows, in order to quantify the outflows, and as well as the storage, these three aspects, if you want to model it, we can use the simulation studies. uh, from my point of view, I can mention, if you have not explored, there is one famous hydrologic modeling called SWAT, right? Soil water and assessment tool. And if you want to simulate a hydraulic modeling, so hydraulic modeling, I will mention a model called HACRUS. Just I mentioned here HACRUS. You can explore these things. Okay. Then there is one more thing, hydraulic routing, is that it is an unsteady process and governed by both continuity and momentum equation. Okay, now moving to the next question here. At the intersection of inflow and outflow hydrograph, when outflow and storage are maximum, it could occur in case of, it could occur in case of I guess this is the same question we have discussed,
Mhm.
don't you think? See, here also the same thing is happening now. Storage is maximum. Again, it is saying that. So whenever the storage is at maximum, whatever
Reservoir?
the inflow will be coming, it will be directly passing as an outflow, and it will be called as
Reservoir
an
routing
uncontrolled
using
distribution.
variable storage. B. Option B. Is it option?
Which one?
Option
B.
B.
Yes, option C will be correct. Yes.
Oh.
So here hydrologic routing is there, and but it is for a reservoir. Okay. Because in that case only you can achieve a like maximum storage if when once the reservoir is filled up to a maximum level, it is not going to hold additional inflow to the reservoir. Instead it is going to pass over that, and in that case you will be having an intersection of inflow and outflow at its peak of what? Outflow hydrograph. Peak of outflow hydrograph, you will be getting an intersection. So see here, this graph you can see here directly. First graph is showing that inflow, and then second graph it is showing that outflow. So in the peak of outflow you are getting an intersection, and at that point it is mentioned maximum storage will be occurred here. At this level maximum storage of reservoir will be done. Now people working nearby the reservoir, whoever they are operating that reservoir, they will be seeing these curves only, and once they are seeing that, there will be some indicator that yes, now the storage is now getting more than the threshold values. So it will be called as an alarm. Now what kind of alarm? Because now people have to open the gates now. Instantly they have to open that gates, because they can't store excess of water after that storage. So these kind of thing will be more useful while we are operating the reservoir. Okay, now moving to the next question. During the passage of flood wave, prism and wedge storage in a channel is. So I hope just I mentioned that these two concepts are useful in Muskingum method. Okay, so it is saying that prism and wedge storage in a channel is. So firstly you have to tell me what is prism storage and what is wedge storage. Any idea with this? I have just plotted a, you can say, a kind of flow kind of scenario. So now from the base to the water level, maximum water level. Okay, if it is normal now, like there is no only whatever the inflow is coming and outflow is going, there is no additional inflow is coming, only called as normal flow. normal flow is happening or passing through a channel. In that case, this whatever the water level you are seeing, it it could be assumed as a constant, and this entire area you can call it as prism. Prism in the sense what? It is not changing. Okay, then if any additional inflow is coming, surplus amount of water is now entering in this cross section, so you could have certain kind of water level change like this. It could distort like this. Okay, in that case, this excess, whatever the excess area you are getting in form of triangle, it could be called as a wedge storage. Am I right or wrong?
Mhm.
So now it is asking about the behavior of these storages when a flood wave is passing. So when the flood wave is passing, then prism and wedge storage will have, what would be the option? Anything, any idea related to this? So here the option is constant and positive during the advancement of flood wave. Look at into this explanation. Okay, so here different stage of channel different stages of channel storage while flood wave is passing. Okay, so channel having a uniform flow, in that case inflow will be outflow. Okay, water surface elevation will be a parallel to the bed of the channel, and this will be called as a prism storage. I just mentioned that that could be possible when the normal flow is there. That normal flow is a uniform flow. Inflow is equivalent to outflow. So this picture is valid for this case. Now see the next one. During the advancement of flood wave, what is happening? As the flood wave enters the channel, upstream water surface elevation become more than the downstream water surface elevation. From this picture you can have better idea that what is happening. So now in this case, inflow is greater than the outflow, and additional storage is being made, and that additional storage is called as wedge storage. I hope now from the picture you may be having an idea that what is meant by prism storage and wedge storage. Wedge storage is just an additional storage over the prism storage, you can see. Now how they are varying, like what is their behavior? So see, if the flood is receding, so as the flood water recedes, in that case water surface elevation at downstream will be higher than that of the upstream. It is now moving, so in the downstream side you are getting a
Higher water
higher
elevation.
value as compared to the
Upstreams.
upstream, right? So in that case outflow will be more and inflow will be less, so results in a negative wedge. It is called as negative wedge. Now second case is flood wave passes through a channel completely. Now it has been passed away, so result is zero wedge. Flood, like whatever the flood wave was there, it has been passed from inflow to outflow and then outflow through to the next downstream part. So there is no storage, no wedge storage is there, and in that case whatever the upstream water surface elevation was there, it will be equivalent to downstream only.
Mhm.
Okay, so the thing was, it was asking that during the passage of flood wave, okay, so here it will be a constant and positive during the advancement of flood wave. Like it is asking about the upstream side only.
Okay.
Got it? just a passing of flood wave, it is saying that. So it is just entering the inflow section. If it is saying that it is receding now, so from this section now the flood wave is about to pass out, so in that case the behavior will be seen at this outflow section. But it is now just entering, it is entering to this section, so that is why it is taken as positive. Okay, now moving to the some numericals. So regarding the Muskingum method, so just now I have mentioned that Muskingum method, in case of Muskingum method, storage is a function of I and Q in the sense inflow and outflow. So there will be some relation which is establishing, like there should be some weightage to I plus there should be some weightage to Q, and these weightage will be done after considering two storages. See this, you have seen this word storage everywhere. So now just in the previous question we have discussed that what type of storages could be possible. So first could be a prism storage and another could be a wedge storage. So giving a weightage to both these storages, we can achieve this kind of empirical relation, and this entire concept have been used in Muskingum method only. So some coefficients, or just I am saying weightage, so weightage are nothing but coefficients. So coefficients have been given. So do you have any idea related to Muskingum method, what kind of empirical relation it is there? Any idea? And what are their relation, like what is the relation between these coefficients? There is a relation between C1, C2 and C3. Three major coefficients have been taken in this Muskingum method. Any idea? Can anyone solve this question? Ma'am, any idea related to this?
I studied long back, so I don't remember. I've not gone through the lectures and so. I'll have to refer, please.
Ashish, any input?
Balamurgan says C1 plus C2 plus C2 is equal to 1.
Yeah, that's good. Yes, Balamurgan, you are right. So yes, this is a simple relation that sum of the coefficients will be equivalent to 1. So now tell me what will be the value. I will be discussing more information about this method in the description, okay, in the explanation part.
Then it's C, 0.2.
Yes, so 0.5 plus 0.3, it will be a 0.8, and then if we are subtracting by 1, then 0.2 will be an answer. Good. So see, routing equation based on Muskingum method. So this equation is primarily used while we are representing the Muskingum method. So Muskingum method, what it is representing, so Qt you have seen. Qt is just an outflow, and it is represented in terms of inflow, like initial, you can say inflow at time t equal to 0 and inflow at time t equal to some interval, you can assume delta t or something, and then q1, that is time, that is outflow at time t equal to 0. So this is an relation. So if we want to know q at time t, okay, after knowing the values, like what are those values, so we have idea about I1, I2. So I1 will be at time t equal to 0, I2 will be at time t equal to somewhat, you can say it is a t. Then we at time t equal to 0 we could also have values of q1. Now we want to know q2. So q2 is nothing but it's a time t. So we can determine this using the Muskingum method. So these coefficients, what are those coefficients which are mentioned in this equation? can be solved using these relations. These relations are expressed in terms of k, x and delta t. Delta t is a time interval. Okay, and then k and x, they are representing, you can say, a weight to, like, in order to transfer a flood wave. So these two parameters are much more representing properties of flood wave while it is passing from inflow to, like, from one section to other section. So what could be, like, what are the characteristics it is changing while a flood wave is passing? That is represented by k and x. Okay, so now you have idea about C1, C2 and C3, and you can compute it from this equation. C1 plus C2 plus C3 equals 1, C3 is 0.2. Now this question you are looking at is related to computing a value, coefficients. Now we want to compute the C1. So in the earlier question you have seen the formula. Note it down. Note this equation. This is an equation that is being asked in this question. C1.
C1.
Yes, C1 coefficient is being asked. See, from this equation also you can see C1 is a coefficient that is used to represent which parameter? Inflow at time t equal to t something, or maybe an unknown time, or where we are predicting the inflow and outflow both. So that is a coefficient. Have you noted this? Should I move?
We have noted down.
Okay. So here, what are the information you have? So x you have, that is 0.3, k is there 4, and time interval, that is delta t, is given 3 hours. Now what was the equation for C1? Tell me. Delta t plus 2kx
Delta t
upon
plus 2.
2k 1 minus x plus
Delta t.
delta t. Okay, now put these values and try to figure it out. How much values you are getting.
K plus 2. Balaram, I'm getting 0.0698.
Okay, 0.0698. That's good. I will check it. I want everyone to solve this. Ma'am, are you getting the answer?
Sorry, sir, I didn't work out. There was a guest. I was disturbed. I'll work out.
Okay, no issue. Yeah, no issue.
I'm getting 0.627.
Point.
627.
Okay,
I'll check it.
I'm writing here. Wait a minute. Point.
Into 0.3 plus 3.
0.627.
I'm checking it again. 1 minute.
Okay, let's check.
2.3.
Okay, so Balamurgan is getting the right answer. So I'm just saying that Ashish, you should look into
Yes.
the calculation again. It should come to 0.0698. Do I need to calculate it?
No, it's okay.
See, what is I'm just writing an equation again. So C1, if you want to calculate, then it will be 3 hours, then 3 minus
Yeah. It's okay. I got it.
how much are you getting now?
1 minute. Minus 2.3.
Okay, wait a minute. Here K value is somewhat changed. It
2.4.
is 4.
Minus
It should be a 4
2.4.
only. And X value is
0.0697. Okay, I got it. 0.0698.
okay, good. Okay, now I'm moving ahead. Okay, there will be one or two more questions related to determining these coefficients, so that you should have idea related to those empirical relations, that how C1 and C2 and C3 are being calculated. So yes, again the question is related to a Mustinger method where you need to figure out C2. So here the values provided here are x equals 0.3 and k is 4 for delta t equals 3 hours. Now see the relation. I am just showing you again. You see here. This is a empirical relation.
C2 is delta t plus 2kx.
Yeah, delta t plus 2kx. Yes. From the above relation C1, there is only a change in the sign.
2k 1 minus x plus delta t.
Yes.
Which is 5.4. 2, 2 is 4. 1 minus 2.3 plus 3. Here into 0.7 is 3. 0.627.
Okay, you are getting point
627. 0.627.
627. Okay.
Yeah.
Okay, so Ashish got this. If Balamurgan got, tell me that answer also. Okay, now it's correct. You are right. 627 is right. So C2 is 0.6279. Ignore these values. X will be 0.3, K will be a 4. Yes. Okay, now compute C3 for the same thing. And tell me what you are getting.
Can we see the formula, please?
Yeah, I'm just showing you. Yeah, see. So here
C3 is equal to 2k 1 minus x minus delta t. Then 2k 1 minus x.
Here the more important thing is to look into the sign, okay, plus or minus, because if you are changing those, then you will be getting a wrong answer directly.
K value is 4 24 to 0.7 minus 3. 4 0.7 plus 3. 8.2. 0.302.
Okay, you are getting how much?
0.302.
0.302. Balamurugan got this answer or not?
Yeah, he also got same answer.
Okay, then definitely okay, no issue. So the answer is 0.302. 0.302, that is for coefficient 3 for Muskingum method. Okay, now we are moving to the next question. That is important question now. Okay, so here see the information related to a river reach. So river reach characteristics are x equal to 0.18, k equal to 4, and the time interval is delta, that is delta t is 2 hours. Route the flood hydrograph through a river reach provided that initial outflow value is 75 meter cube per second. So initial value is being given directly. The attenuation is, it is saying, it is asking that attenuation is. So attenuation will be what? It will be a difference between, difference in the peak of inflow and outflow. So inflow, peak of QP of inflow and QP of outflow. If you have this information, QP of outflow and QP of inflow, you can subtract them and you can get the value of attenuation. Just from the picture you can have idea that yes, this is a one inflow hydrograph, and then again there is a outflow hydrograph plotted. This is a peak of inflow and this is a peak of outflow. Now if you take a difference of this is called an attenuation in the peak. Attenuation in the peak. Any confusion with this?
Downfall of the. Okay.
Yes, because peak are now it is getting reduced. Why it is
Reduction in peak.
yes, right. So here we have to compute this attenuation. So if we what data we have, see, so we have a data related to a inflow to the river reach. So we have information related to a inflow hydrograph. Make it sure to you that we have information related to inflow hydrograph only. So with the time inflow have been recorded and we don't have information related to outflow. But in order to compute that outflow, we have been given some additional information like river characteristics, flood wave characteristics, xk, as well as duration of the flow or duration of the flood passing through the reach. So after looking these information, we can we could have some idea that we need to use certain method with which we can calculate outflow hydrograph. So we need one method through which we can compute the outflow hydrograph. So like whenever we are trying to compute some new hydrograph using some inflow information, that is only called routing. So here routing method will be used. And which routing method? So here hydrologic routing method will be used, because those characteristics are being given. So Muskingum routing method will be used here. We will use the Muskingum routing method. So using the Muskingum routing method, firstly we will try to compute the outflow hydrograph. Once we got the outflow peak, the peak of the outflow hydrograph and peak of the inflow hydrograph, we will subtract them and we can have attenuation value. So now just I mentioned that we need to figure it out the maximum value of both these graphs. So for inflow, whatever the data you are looking into the picture directly, can you tell me what is the maximum inflow value you are seeing and at what time?
Maximum 685 at 9 hours.
Yes,
Yeah.
good ma'am, right. So its maximum value is Q of peak at inflow. So it is, we already got the value 685. Now what left? So Q of peak of outflow we need, and we don't have information related to this. So for this case we need to use the Muskingum routing method, and we will try to get the value, and then we will see the maximum value of this for entire stretch of period 1 to 20 hours. So what is the, can you tell me the equation for routing of Muskingum method? So I just mentioned there while we were solving the coefficient. So Q2 can be expressed as C1 I2 plus C2 I1 plus C3 Q1. It could be represented like this. Okay. So Ashish, if I am
Yes.
considering, if I want to compute Q2 in the sense what? I'm just saying that it is saying that initial outflow is 75. So from this graph you should have idea that this is a initial outflow value. This is an initial outflow value. This is an outflow value, like it could be Q1. You can take it as Q1. So now you have idea about Q1. Any doubt in this? Ashish, any doubt in this?
No.
Because it is mentioned in the question only, na? Yes. Now, do you have any idea related to I1 inflow at initial time? What will be the inflow? It is directly given in the question itself. At 1 hour, what is the inflow?
75.
Yes, so I1
75.
here it will be at 75 only. What about I2? I2 will be inflow at time t equal to 2 hours.
Yes.
So it will be 105. Now what left? C1, C2, C3. So firstly what we have to do? We have to compute the coefficients first. C1, C2 and C3. Now
Okay.
your first task is to compute C1, C2 and C3. Then only we can solve for Q2. And then likewise we have to compute for Q3, Q4, Q5, Q6 up to Q20.
Okay.
After looking these continuous values from Q2 to Q20, we could have idea that among these Q values, I am having maximum, this much of maximum value, and we will take this value and we will subtract with 685 and we will get the attenuation. So our first task is to quantify the coefficients. So C1, C2 and C3. So what was C1? Can anyone tell me the what was the relation to them to that?
The C1 is
What was the relation?
delta T plus 2kx.
Delta T plus 2kx upon 2k 1 minus x plus
Delta T minus 2kx, I think.
minus 2kx.
Sorry, minus
Okay, minus
2kx.
2x, and in denominator it will be a plus
2k into 1 minus x plus delta.
Plus, it will be plus delta t, right?
Yes.
Yes.
Okay, so now we have to compute that C1. So directly tell me the value now. Compute it fast.
Yeah, Balamurgan already calculated
How much it is
0.0654.
getting?
0.0654.
0.0654. Okay, now what
Yes.
about C2? C2 will be
C2
a change in sign
is
only.
there.
So delta T plus 2kx upon 2kx, sorry, 2k1 minus x plus delta T. Now tell me the value directly.
So C2 is 0.4018.
0.4018. Got it. Then what about C3? So C3, what was the
C3
equation? So 2k1 minus x minus delta t upon 2k1 minus x plus delta t.
0.5328.
Okay, you got this value. How much? Point.
Balamurugan calculated this one. 0.5328.
Okay, whatever the values you are saying, you have
Yeah,
calculated
yeah,
that.
yeah. Yes, it's calculated
Okay,
by Balamurugan.
what is the value for C3?
0.5328.
0.5328. Okay, let's check.
Yeah, I'll take it.
Okay, what are the values you just mentioned? Whether they all are correct or not, you can check here.
Yeah, 0.5328 is correct. 0.4019 is also correct. And just a
C3,
minute. 0.0654 is also correct.
all correct?
All correct.
Yeah, good. That is good. Now we from the equation what we were having at that time, Q2 equals C1, we got the information, so I can write it directly. So 0.0654 I2 plus 0.4019 I1 plus 0.5327 Q of 1. I can write it as like this, right?
Mhm.
Now I also have information related to Q1. Q1 is 75. I1 I already got 75 and I2 is 105 something. Now compute Q2, how much you are getting.
10654. Okay, 18.
See, today I am not having a calculator with me. Okay, so
No
whatever
issue.
the calculation I will be directing you, you should calculate that. So see here, you have to compute this Q2 value here for time t equal to 2 hours.
So Q2 Balamurugan calculated 76.96. It's correct.
76.96.
Yes.
It is correct. Good. So
Hmm.
likewise you have to calculate for Q3. Okay, then Q4, because what will happen now if I'm saying you that I'm now switching for Q3. Okay, so here again what will be the, like, from this equation you can see, if I have just computed Q2, now I want Q3. So what will be the input for this? 0.0654, it will be a I3 now, plus 0.4019 I2. Don't you think it will be I2? Because we want next value na, Q3,
Hmm.
more higher value, then we have to adjust these coefficients, oh sorry, these input parameters also, but coefficient will be same. So at that time while we were calculating the outflow for t equal to 2 hours, we were using an inflow at t equal to 2 hours and inflow at 1 hour, that is the initial values, and q1. Now we are
Hmm.
adjusting likewise only 0.5327
Okay, got
and
it. Got it. Got it.
what,
Yeah, I got it.
got it now, no issue.
Yes.
So
So
compute
likewise,
this
we
value
increase.
Q3,
Yeah. Mhm.
how much you are getting.
1 minute.
See, this table is being divided in dividing those parameters, like which are being uh, sum up together. It's been divided in columns, like from this you can see the columns. So this is one column, this is a second column, and this is a last column. And then we are getting the Q2 value. Q2, how we are getting? Q2 we are getting by adding C1 I2 plus C2 I1 plus C3 Q1. Ashish,
Yes.
I'm just saying, take whatever the value it is mentioned here now. That is Q2. Where is my cursor? Wait a minute. Yes. This Q2, you need to take it from the value you got at previous step. Okay.
Previous step. Okay.
Yes,
Follow.
yes. That is a Q2 only. Don't confuse with that. Because here it is Q2. That is 76.96. You have to use that value only. So Q2 is known to you. I2 is there. Uh, no, that will be I3. So I3 is known to you. That is 165. And then what left? I2. So I2 you already have 105. Do you got this value?
One minute. 3, I2, and Q2. Q3.
Not getting the answer.
1 minute, 1 minute.
I'm unable to work very fast, so I'll do it after you finish and post. I'll
Yeah,
do it
okay,
because
no
I,
issue.
I I don't have a calculator. I'm doing it in my mobile, so it
No
takes
issue.
little time.
Yeah, okay. Let me calculate from myself too.
Just point 654. 1 minute. Point
Point
0654.
00654 multiplied by I2. So I2 will be
06.
okay 6.
I do is 160, 105. Okay, I did this mistake.
Wait a minute.
0.401.
I'm also calculating. 30.14, 9.95. Zero point 0.0654 multiplied by 65. Okay, so I'm getting 10.79. What is the problem? I'm getting this value 6.979. Ashish, what like at I2 you have to take this value inflow at 3 hours, so that will be 165.
Mm-hmm.
Okay, and
I took in 165, 105 for I2,
that's good.
I3, and then the Q2 is 6.87.
How much? 6 to Q2?
6 point, oh, I did this
No, no,
mistake.
no, no. You have to use this Q2, na? This 76.96. Whatever value you got, it is earlier
Okay,
step. Final
right.
value.
Hmm.
Why you are getting confused? That is an
Yeah, yeah.
outflow value. This one. This Q2.
Hmm. Got it.
I am writing it again. See, I3 will be 165, I2 will be 105, and Q2 will be 76.96.
Hmm.
Now if I am moving ahead to the next step, then I4 will be 275. Wait, okay. And then I3 will be 165. Then okay, Q2, or no, no,
Q3,
Q3
Q3,
will be 93.99.
93.99.
Whatever the
Oh,
value
got
you
it.
are getting at this step.
Yeah. Yes, I got it.
Okay, tell me whether Balamurgan got this or not.
Yeah, he already written answer is 5.83 meter cube per second.
That's good. Okay, so see, Ashish, you can follow this step
Hmm.
likewise for all these time steps, and you can
Hmm.
see we would get some maximum value at time
Hmm.
t equal to 11 hours. We are getting this value,
Hmm.
and after that these values will be getting receded. Like now the flood is now passing away, so that's why whatever the values now you are getting, it is getting receded, it is getting
Hmm.
lowered
So this is peak
or
outflow and peak
reduced, you can
inflow.
say.
Yes, I got
So
it.
now what is being done, I have taken this column and I have taken inflow column, both. Using these two columns, this graph have been plotted. Okay, and you can see from this graph maximum peak you can see. Even if you don't want to plot, there is not a mandatory thing, it is just for your uh, visual
Understanding.
yeah, right, it's for your understanding. So yes, from this graph also you can see the maximum value, and you already have maximum value of inflow peak, that is 685. Taking a difference of both of them, you can get a value of somewhat 50.83 meter cube per second. Okay, now I'm moving to the next question. So question is bit more similar, provided the difference the question is asking is that we need to figure out the peak time delay for this flood. Okay, so attenuation you got it right, then it is asking about the delay which is being done. Okay, so whatever the values you got after plotting this, the similar procedure, like whatever the C1 values we are getting C2, we are getting C3. Okay, and at the last you can see the difference. It is being seen that for an inflow, what was the time? It was like time was how much? It was 9 hours, right?
9 hours.
Yes. Now we are at an outflow, and maximum peak for outflow is being seen at what time?
11 hours.
11
11
hours. Yes.
hours.
So now what will be the delay? So delay in the sense delay in their peak. This is the delay. Got it? This is a delay.
Yes.
So we need to
Okay.
subtract this and we can directly get 2 hours. Got it?
Okay, got it.
Okay, so this much was the discussion for today's session. Uh, I'm sorry actually for the whatever the time lost in the earlier case, like it is
No issue.
already lost half an hour. Okay, because there was
It's
some.
okay. One more small information. 3 problems what we worked last week are wrong.
What?
I don't know how. I wonder. Last week assignment problems what we discussed and worked, no?
Yes.
3 answers are marked wrong.
Okay. Ma'am, what were those questions? Can you tell me?
1 minute, I'll tell you.
Yes.
I'll refer my Swayam assignment and tell you. Just a minute.
Yes.
That is 10, 11, 12, I think.
Maybe he's correct. I'll just confirm.
10, 11 and 12.
Mhm.
Okay. What like can you tell me the concept that in what was their concepts in which those questions were based?
No, we just get the reply that the answer is incorrect. Shall I give you the range of answer or whatever?
Yes.
For 11th problem, I mean, 10th problem, the answer is set 62.72. We
Okay.
found a mistake and we corrected and we got it as 32.04, right?
Yeah, correct.
Okay. Okay.
But that is marked incorrect for us for the 10th problem.
What was the
Then
question?
11th,
Can you read their
the-
question so that I can?
yeah. Watershed A having the 2-hour unit hydrograph derived from the observed rainfall and runoff of an isolated storm on it has following characteristics. Basin lag 24 hours, similar to the one you started discussing today, right?
Okay.
And then peak discharge 50 meter cube per second, area 700 kilometers square, L 30 kilometers, LC 15 kilometers. We worked out in detail last class.
Okay.
We got the answer 32.04, but they say the accepted answer is 62, range is 62 to 72.
Okay. Okay.
Then the 10th one, we got 66.45, almost continuation or similar, watershed A, B, watershed B.
Okay.
Almost the same problem continued. We got an answer of 66.45, New Therapy, 66.45, but they say the range is 29 to 34.
Okay. Okay, ma'am. Sure, ma'am.
So that is also marked incorrect.
So 10th and 11th.
10, 11, 12, 12 also. 12 also is marked incorrect.
Okay. Okay.
12 we got, see 12 also watershed A, B problem.
Yeah.
We got an answer of 208.24, but their range is 90, 100 accepted answer.
Okay. Okay. So, ma'am.
So all 3 came
I
wrong.
will go through those questions. I will solve it from my side, and then.
Yeah, please check.
Yeah, sure, ma'am. And then we will discuss it in the next class.
Okay.
Yeah.
Thank you.
Yes, ma'am.
Thank you very much for your efforts.
Ashish,
Yes.
anything you want to discuss today?
Yeah, we can discuss in next. We are still working on that report
Yeah,
and
done. Okay, no issue. That's good. maybe it may be possible that I will be taking the next class from Vienna itself, because I'm having a flight on 11th. So definitely,
So if you have a time issue,
there will
you
be,
can provide us any time in between. We can manage.
yeah, sure. Actually, that will be communicated from NPTEL team side. They will raise whatever the schedule will be possible. Okay, I will discuss with them.
Mhm.
Okay,
Okay.
yeah. Okay, then I will
Okay,
All,
thank
all
just
the best. All the best
all
for
the
your
best. Yes,
presentation.
yeah.
yes.
Thank you so much, ma'am. Thank you so much.
Okay.
Yeah.
Have a safe journey and thank you.
Yeah, yeah.
Thank you
Enjoy
so
your
much.
trip.
Thank you.
Mhm.
Thank you, Balamurugan. Thank you. Okay, then we will meet in the next session. Yeah.
Thank you. Thank you.